Section 10.6 is alternating series and absolute and conditional convergence. You are going to want to have your summary of tests for series out because we're going to be adding some things for the alternating series. I'm going to let you add some notes to this sheet. So if you have it with you today, please go ahead and take it out. And what we're going to be adding to it is going to deal with the absolute and conditional convergence. So when we get to that, I'll tell you when you can add things and what you can add to your formula sheet. Theorem 14 is the alternating series test. It's also called Leibniz test. And this says that if you have a series whose terms alternate, so it's an infinite series starting here at n equals 1 and going to infinity, you know it's going to alternate if you have a negative 1 raised to a power. When that power is even, your terms are positive. When the power is odd, the terms are negative. And then you're going to have some function of n here. So the terms of your series are going to alternate either positive, negative, or negative, positive. The first thing you have to do is to be able to identify what an alternating series is in order to use the alternating series test. The alternating series test says that this series will converge if all three of the following conditions are satisfied. First of all, the absolute value of the terms have to be positive. We know that there's going to be negative terms because of this. This is what makes the terms negative or positive. So this affects the alternating signs, and these have to be positive. The positive u sub n's are eventually going to be non-increasing. We say eventually because it doesn't matter what happens at the front of the series. So if I have a series and the terms are starting out, increasing, at some point they're going to be non-increasing. So what that means is that u sub n is going to be bigger than the next term, u sub n plus 1, for all integers or for all values that are beyond this point. And then the last condition is that the limit as n goes to infinity of u sub n is going to be equal to 0. Well, our nth term test for divergence tells us that's the case, right? If this condition fails, then our series is going to diverge by the nth term test for divergence. Another way of writing this limiting notation is using the limit. In example 1, we're told to use the alternating series test to determine the convergence of the alternating harmonic series. The first thing you should notice or you should point out is that you do have an alternating series. On a test, if you're going to use the alternating series test, the first thing I want you to notice is that we do have an alternating series because we have negative 1 raised to the n plus 1. Once you've identified that you have an alternating series, typically this first thing I don't check because it's going to be the case that these terms are going to be positive if n is equal to 1 to infinity. More often than not, that's the case. If not, you could factor a negative out and then stick it into this term. So I don't really force you to show this first thing. These other two conditions I do ask you to show. I need to check two things. I need to check first of all to see if it's non-increasing, and then the next thing I need to check is that the limit as n approaches infinity of a sub n is indeed equal to 0. So we have a harmonic series. Remember, the harmonic series looks like this. What happens to a fraction as n gets bigger? The value of the fraction gets smaller. So you can either graph this to show that it's non-increasing, or you could just look at it and observe. When it's as obvious as this, I would recommend just looking at it and observing. As n gets bigger, when the denominator gets bigger, the fraction gets smaller. Then the next thing we have to check is the limit as n approaches infinity of 1 over n. Is that equal to 0? And the answer is yes, because this ends up being 1 over infinity, and 1 over infinity is 0. Therefore, we would conclude that the alternating harmonic series converges by the alternating series test. The alternating series test is not difficult. We've only got to check really two things, these two things right here, that the terms of the sequence are non-increasing and that the limit is equal to 0. If that happens, then we say that our series converges. But what about this series right here, just the harmonic series? What would we say about this series? The harmonic series is a divergent p-series. Look at your formula sheet. For a p-series, we said that if we have 1 over n raised to a power, if that power is equal to 1, then the series is going to diverge. But when we stick that negative 1 raised to a power in front of it, we see that the series converges. What causes something to diverge? The terms don't get small enough fast enough. The sequence doesn't go to 0 fast enough. So what is it that makes the alternating series converge whenever it doesn't alternate, it doesn't converge? Well, let's look at a graph of what the terms of the alternating series would look like. So if we have an alternating series and the first term is positive, then if we start at 0 right here, when I add the first term, I'm going to stop right here at my first partial sum. The next term is going to be negative because the signs of the terms in the series alternate. And it's decreasing, which means that the terms are getting smaller. So the length of these line segments is going to get shorter. So when I look at my second partial sum, it's going to be bigger than 0 because I took away u sub 2 from a positive u sub 1, and u sub 2 is not as big as u sub 1. The next term is going to be positive, but it's not going to be as long. Using this length of the line to represent the term, it's not going to be as long. So my third partial sum is not going to be as far out as my first partial sum was. Then the next term is going to be negative, so I subtract. And what we see is by adding and subtracting these terms that are getting smaller and smaller and smaller, we end up converging to some limit. That limit would be the sum of our alternating series. Can you see now why the alternating harmonic series converges, but the regular harmonic series does not? The terms of this series don't get small enough fast enough, but by causing them to alternate, I'm actually going to be approaching some limit. So that's why the alternating series converges whenever the straight harmonic series does not. Example 2, we're asked to use the alternating series test to determine the convergence of this series. The first thing you need to note is that this does indicate that we have an alternating series. What are the two things we need to check? First of all, are the terms of the series decreasing or non-increasing? And then the next thing we need to check is the limit as n approaches infinity of a sub n. This we can check just simply by graphing the function. When you type in your series, be sure you pay attention to the parentheses. You want to get the parentheses right. Otherwise, you'll end up with the wrong graph. So looking at the graph of this function, this is the function that I graphed over this window. We can see that it is going to be non-increasing, so we're going to say that the first condition has been checked. On your test, you do need to check it, because if you get it wrong and you say you checked it but you didn't, I'm going to count off, because if this condition doesn't hold, we can't use the alternating series test. Then the next thing we need to check is the limit as n approaches infinity. So I'm going to look at the limit as n approaches infinity of 4 divided by the natural log of n squared. Well, as n goes to infinity, that's the natural log of infinity, and we know that goes off to infinity. Square an infinity, you get an infinity. 4 divided by infinity is 0, so that condition checks. So since both of those conditions are satisfied, we will conclude that our series converges by the alternating series test. But you have to show that you checked these two things. You can't just look at a problem on a test and write the word converges or diverges. Remember, for this test, it's not the final answer I'm grading as much as I'm grading the work it took to support that final answer. I'm still grading the final answer. If the final answer is wrong, the problem's wrong. But you've got to show the work to support the final answer. This shouldn't be example 2. This should be example 3. We want to use the alternating series test to determine the convergence of this series. The first thing we notice is that we do have an alternating series. And then the next thing is we need to check to see if the series is decreasing and the limit as n approaches infinity of a sub n is equal to 0. It looks like this series might be decreasing, but what else does it look like? It looks like this is going to fail, because when we look at the limit as n approaches infinity of n squared plus 5 over n squared plus 4, what is that limit equal to? It's equal to 1, because the degree of the numerator is the same as the degree of the denominator. That means this condition fails. What that tells us is that the alternating series test is inconclusive. What we can conclude is that this is going to diverge by the nth term test. If this condition fails, then odds are this is going to diverge by the nth term test. Now we're about to get to the point where I said you can add things to your formula sheet. The next thing we're going to talk about is what conditional and absolute convergence are. We say that a series converges absolutely if the corresponding series of absolute values also converges. And then a series converges conditionally if the series of the absolute values diverges. So another way to think about this is that if you have an alternating series and the series converges when you take that -1 that causes it to alternate away, then we say the series converges absolutely because the absolute value of the series also converges. If the absolute value diverges, then we say it converges conditionally based on the condition that we have that -1 to the power in the series. Example 1, remember, was the alternating harmonic series. And when we did example 1, we said that that series converges by the alternating series test, but when I took the -1 away, we had a divergent p series. So now we can carry things a step further and say that this series converges conditionally because when I took the -1 to the power away, we ended up with a divergent p series. So this would be an example of conditional convergence. On the summary of the test for series, underneath the alternating series, I will let you add a note because the alternating series test never shows you whether or not something diverges. I'll let you add a note in here about absolute and conditional convergence if you like. You only have to investigate absolute and conditional convergence if your series converges. So for this series, do you think that it would converge absolutely or conditionally? If we took that -1 away, what do you think would happen here? Well, I think it's going to converge. I'm not going to take the time to show you this, but if that converges, then we would say that that series converges absolutely. Because this series diverged, we didn't have to check for absolute or conditional convergence. Anytime you have an alternating series that converges, you've got to check to see, does it converge conditionally or does it converge absolutely? In example 3, that's what we're going to look at. We want to determine whether the following series converges absolutely, conditionally, or diverges. So for part A, the first thing you want to notice is that we do have an alternating series. We need to check these conditions. So this is going to be 1/10 raised to the n. It might be a good idea if we rewrite this series so that we can see it like that. So this is going to be the sum, n equals 1 to infinity, of -1 raised to the n plus 1 times, this is going to be 1/10 raised to the n times 1 over n. As n gets bigger, this fraction's going to get smaller and this fraction's going to get smaller. We are going to end up with a decreasing terms in our series, so that condition is met. Furthermore, as n goes to infinity, we've got the limit as n goes to infinity of, well, another way I could write that is 1 over 10 to the n times n. As n goes to infinity, this is going to go to 0, so that condition is satisfied. Because both of those conditions are satisfied, that means that we have a convergent alternating series. Because the series converges, I then need to check the convergence of this series. And I think it's easier to see if I write it as 1 over n times 10 to the n. Do you see that this series is just this series without the -1 raised to a power? That 0.1 to the n is 1/10 to the n, so there's my 1/10 to the n, and then divided by n, so I keep that in the denominator. How can I check the convergence of this series? What can I try? Do y'all remember the ratio test? The ratio test says that you want to look at the limit as n goes to infinity of a sub n plus 1 over a sub n. So my n plus 1 term is what I'm going to get when I replace n with n plus 1. So that's n plus 1 times 10 to the n plus 1, which is just going to be 10 times 10 to the n. And then I divide that by a sub n. Well, dividing by a fraction is the same thing as multiplying by the reciprocal. And then we look to see what's going to cancel out. The 10 to the n's are going to cancel. I'm left with the limit as n goes to infinity of n over n plus 1 times 10. And I'll just write that as 1/10. Well, as n goes to infinity, this is infinity over infinity. That's an indeterminate form. The degree of the numerator is the same as the degree of the denominator. That's going to be 1 times 1/10. And for the ratio test, we said that that's going to converge. The series will converge as long as that is less than 1. So we would say this converges by the ratio test. And so this alternating series would have what type of convergence? Is it absolutely or conditionally? Absolutely, because when I looked at the series of the absolute value of this, it converged. So we would say this series converges absolutely. The steps we took was first we identified we had an alternating series. We checked to see if the conditions were satisfied for the alternating series to converge. Once we determine the alternating series converges, then you need to check the series without the -1 raised to the power. And I rewrote the terms in this series in a form that would be easier for me to work with. Then we checked the convergence of this series by using the ratio test. The ratios test says that we look at the limit as n approaches infinity of a sub n plus 1 over a sub n. We saw what canceled out. We saw that that limit was equal to a number less than 1. That meant that the absolute value of our alternating series converged by the ratio test, and since the absolute value converges, our series right here converges absolutely. Let's look at another one. So the first thing we're going to notice here is that we do have an alternating series. Then you need to check to see if your series is going to be non-increasing, and then also check the limit as n goes to infinity of a sub n. Discounting that -1 raised to the power, a sub n here is going to be 1 over 1 plus the square root of n. As n gets bigger, the value of this denominator gets smaller, which means that the terms will be decreasing. So that condition is satisfied. Furthermore, when we look at the limit as n approaches infinity of 1 over 1 plus the square root of n, we see that this is going to be 1 divided by infinity, and that is equal to 0. So this condition is satisfied, which means that we have a convergent alternating series. To determine if the series converges conditionally or absolutely, we're going to check the convergence of the series without the -1 raised to a power. So we're going to check the convergence of the series n equals 1 to infinity of 1 over 1 plus the square root of n. What test might we use to check the convergence of this series? P-series? We can use a p-series to compare to. Let's try the limit comparison test. It's not the only test that'll work, but it's one that's easy and I like it. Remember, in the limit comparison test, we're going to compare the terms of this series to a series that we know either converges or diverges. When you use the limit comparison test, I said you got to be careful what you compare to. If we strip away the constants here, I would want to compare to what? If I strip away the constant plus 1 in the denominator, I'm left with 1 over the square root of n. We have to know whether or not this series converges or diverges. What do we know about this series? This is a divergent p-series where the power is 1/2. Remember, when we look at p-series, our series is going to diverge if the power on the term in the n in the denominator is between 0 and 1, then your series diverges. So 1 over the square root of n is the same thing as 1 over n to the 1/2. 1/2 is less than 1. For the limit comparison test, we're going to look at the limit as n approaches infinity of our series, 1 over 1 plus the square root of n, divided by the series we're comparing it to. Well, dividing by 1 over the square root of n is the same thing as multiplying by the square root of n over 1. So I could rewrite this as n raised to the 1/2 power over 1 plus n raised to the 1/2 power. And what is that going to be equal to? The degree of the numerator is the same as the degree of the denominator. So it's just leading coefficient over leading coefficient. That limit is equal to 1. For the limit comparison test, we said that if we compare to a known series and we get a finite number, then both series are going to do the same thing. So if we compare our series to a series that converges, then we're going to converge. If we compare our series to a series that diverges and we get a positive finite number, then our series will diverge. In this problem, we compared to a divergent p-series. So what does that tell us about this series? Because this limit is equal to 1, both series are going to do the same thing. I compared this to a divergent p-series, so our series right here are going to diverge. So we saw that we had a convergent alternating series, but the absolute value of that series diverged. So we would conclude that this series converges how? It converges conditionally. So if the alternating series converges, but the absolute value of that alternating series diverges, you have conditional convergence. If you have an alternating series that diverges, you don't have to worry about checking for conditional convergence because it diverges. And this wraps up section 10.6.